When you look up at the stars, what do you see? Our earliest ancestors saw a blanket of darkness draped across the heavens by the gods, a vault holding back the wonders of another world. These stories eventually gave way to a more modern understanding of our world when scientists began seeking answers about our planet, our solar system, and our universe. And while science seeks to understand the universe around us, science fiction explores the possibilities of living in that universe. But how do we actually get there? Hi, my name is Eric, and this is Sci-Inspiration. This is the first in a series of 2 videos on the science behind space travel in science fiction. There are 2 classic examples of science fiction that nearly everyone is familiar with. Star Trek, which first debuted in 1966, and Star Wars, which first premiered in 1977. These both do a fantastic job of exploring what it would be like to live in space, but they had a problem. The universe is big, like really big. So both shows had to come up with something to make space travel reasonable. In Star Wars, ships traveled between the stars using hyperspace, while Star Trek's ships travel via the warp drive. And while there are numerous video games that also explore these same concepts, I want to talk about Elite Dangerous. In Elite Dangerous, commanders are given the freedom to make their fame and fortune throughout the universe. They may choose to do so through trade, smuggling, bounty hunting, or charting undiscovered solar systems. But once again, the gargantuan size of the universe means that Elite Dangerous also has to come up with a way to quickly travel between the stars. Their answer: the frameshift drive. Here, I'm traveling between 2 star systems nearly 7 light years apart, about 65 trillion kilometers. Whereas this trip would normally take thousands of years, with the frameshift drive, it only takes 15 seconds. This means that my ship traveled 15 quadrillion kilometers per hour, 14.5 million times the speed of light. For comparison, the fastest humans have ever traveled was when Apollo 10 launched on May 18, 1969, and reached a speed of 40,000 kilometers an hour, 256 billion times slower than the frameshift drive. Now, before I talk about how the frameshift drive works, let's give ourselves a baseline by figuring out how long it would take to travel from Earth to our nearest star, Proxima Centauri, a mere 4.25 light years. When spaceships burn fuel, they exert a force that propels them forward, but humans can only survive so much acceleration. The highest acceleration survived by a human for a prolonged period was nearly 50 times the acceleration of gravity, when John Stapp, a US Air Force officer, strapped himself into a rocket sled and was accelerated to over 1,000 kilometers an hour in 1954. If we can't safely exceed this 50G acceleration, it would take a whopping 209 days to reach Proxima Centauri. That doesn't sound like a lot, but bear in mind, that's 209 days of this level of acceleration. And somehow, I don't think a lot of people are going to sign up for that. Unfortunately, there's another problem. So far, we've only been thinking about this in terms of Newtonian physics, the rules that you might have learned back in high school. An object in motion stays in motion, force equals mass times acceleration, and every action has an equal and opposite reaction. While these principles do a great job of describing how things work on Earth, they start falling apart when moving near the speed of light. We need to bring in a second set of principles, Einstein's theory of relativity. You've probably seen this equation before. The E stands for energy, the M stands for mass, and the C is the speed of light. A common misconception is that this is just a conversion ratio between mass and energy, but that's not 100% correct. To really understand this equation, it helps to rearrange it into its original form. Now, what this equation states is that mass is a property of energy. This results in some interesting behavior. When an object starts moving faster, its kinetic energy increases. Because mass is a property of energy, the object actually increases in mass by a tiny amount. But because the mass is increased, it requires more energy to accelerate, which increases the mass of the object further, which requires even more energy to accelerate, and so on and so on. Eventually, if the object were to move at the speed of light, it would have infinite mass, and would therefore require an infinite amount of energy to make it go any faster. So, because the fastest our ship can theoretically travel is just under the speed of light, our trip to Proxima Centauri would still take that 4.25 years. To complicate things further, it takes a lot of energy just to get stuff out of Earth's orbit, let alone accelerate it near the speed of light. For example, NASA's New Horizons space probe, which only weighs 30 kilograms, required a nearly 450 kilogram rocket when it launched back in 2006. It then took 9.5 years for it to pass Pluto and leave our solar system. With our current technology, sending a human outside of the solar system is just not possible. At least, for now. There are some theories on how we could develop faster-than-light technology, but those will have to wait until next time. Hey, thank you so much for watching. This episode's science shoutout goes to Neurotransmissions. Neurotransmissions is a fantastic YouTube series that explains neuroscience topics in an easy to understand and approachable way. With the recent release of Star Wars: The Last Jedi, I recommend checking out their video where they talk about all of the science that would go into making Luke Skywalker's prosthetic hand. If you enjoyed this video, please give it a like down below. In the second part of this series, I'll explore the more theoretical technology that shows up in Star Trek, Star Wars, and Elite Dangerous, so be sure to subscribe if you don't want to miss it. Until next time, stay inspired.